So here we are. We're going to do a next example of a inverse function. Incidentally, I've done it in this question wrong on my repeat. Trying to do it right this time. So if I have a function g of x is equal to x squared plus 3, I quickly make a sketch of that. What I note is my vertex is 0, 3. If I look at my function g is not 1 to 1. That is, the inverse will not be a function. I need to restrict the domain so that it's a function. So probably what I would like to do is to make my function 1 to 1. The easiest way to make my function 1 to 1 is simply cut it in half and include only one arm. What arm I'm going to say? Well, I'm going to make it the positive arm. And when I say the positive arm, I mean the right arm. So here it is. I'm going to find the inverse function of g of x is equal to x squared plus 3. Now, it's important to think of it as the positive arm, and we'll see later. Algebraically, I'm just going to start to derive this, if you don't mind. I replace with my functional notation with y. Easy enough. With inverse functions, I swap out my x's and y's. There it is. So I'm just going to say swap x's y's. So there we have it. And this becomes from my mapping notation xy becomes my point y x. Really big theme that the x's and y's switch. This carries on, has many, many consequences. So anyways, regardless, right now, this is the inverse. So I am going to try to algebraically isolate for y. And when I do that, this is all looking good. The algebra is fairly straightforward, I think. So I'm going to subtract 3 from both sides. Now I'm going to bring up my work over here. So y squared is equal to x minus 3. So now I have y squared is equal to x minus 3. I'm going to take the square root of both sides. And when I take the square root of both sides, please remember from last year, you have to consider both positive and negative roots. So here's the hitch. Since I was only including the positive arm, I now only include the positive root. Maybe you want to write that down. Last but not least, I'm just going to reintroduce my functional form, and I'm going to call this g inverse is equal to the square root of x minus 3. Now look, let's take a look at the instructions. We are going to square the input, then add 3. And our input in our inverse function, what does the instruction say? Well, you're going to take your input, subtract 3, then take the square root. It almost makes sense. But that's the inverse function. All right. Next one. Try h by yourself. Hi, welcome back. I think I quickly put this together. It looks pretty good to me. And what I get is I reach the point where, or a certain point, where y is equal to, or y squared is equal to x plus 2. So when I take the square root, y is equal to plus or minus the root of x plus 2. Anyways, since I've only included my arm, like if I was to make a very quick sketch of this, what I notice is that I have vertex 0, 2. Sorry, 0, negative 2. And I have put the restriction on it like, hey, I'm only keeping my positive arm here. So since I'm going to keep the positive arm, I'm only going to keep the positive root. So I'm only going to keep the positive root right here. So my inverse function would be h inverse of x is equal to the square root of x plus 2. All right. Next. Oh my. Oh my. Here we are. We're going to make a quick sketch of this graph. There it is. There's y is equal to x squared minus 2. And what's interesting about this is I'm only going to keep the negative arm. Well, how does this differ? Well, the algebra, well, hold on. Whoa. I'm only going to include the negative arm. There it is. You do the algebra. And what you'll notice is that at one point you'll get y is equal to the square root of x plus 2. And it's going to be plus or minus. Let me just do that again. Now, how am I able to do this so incredibly quickly? Well, it's the exact same question as before, except for the original domain is restricted. So y is equal to the square root, positive and negative square root, of x squared minus 2. However, we are only looking at the negative arm. So in this case, we are only going to consider the negative root. So here are some insights. You can find the inverse of a relation by interchanging the x and y coordinates, specifically xy maps into yx. The graph of the inverse relation can be obtained by reflecting about the identity line y is equal to x. So that is called the identity line. Now, I haven't touched on this, but it should make sense. The domain of my function, the domain and range of my function relation become the range and domain of my inverse. Since the x and y's swap, same with the domain and range. A relation has an inverse function if and only if the relation is 1-to-1, passes the horizontal line test and the vertical line test, both. I know I only wrote one, but it's actually both. And any 1-to-1 function has an inverse function. When the inverse function, or when the inverse of a function f is a function, it can be called an inverse function and is denoted only then as f inverse. At times, you and I are going to have to restrict the domain of f in order to create a 1-to-1 function. And that's all I have on inverse functions.